All right, I want to draw three different types of fields here. The first field is going to be a downward field, and it's going to be a gravitational downward field. The second field that I'm going to draw is going to be an electric field, also downwards. And the third field that I'm going to draw is going to be a magnetic field, also downwards. Now, I'm going to draw in each field three particles, three negative particles. The first negative particle, I'm going to call particle 1. It's at rest. The second one is also at rest. We'll call it particle 2. The third one is also at rest. We'll call it particle 3. So we have a stationary, negatively charged particle in each of these fields. The second particle I'm going to introduce, the second type of particle, the fourth overall particle, is going to be moving. It's also going to be a negative particle, but it's going to be moving to the right. Call that particle 4, particle 5, and particle 6. And finally, the last group of particles that I'm going to draw here are going to be negative particles again. This time the negative particle is moving downwards. Particle 7, particle 8, and particle 9. I want to know what happens to each of these particles, particles 1 through 9. Particle 1 is a stationary negative particle in a gravitational field. What happens to it? It experiences a downward force as a result of gravity. It has mass. Things with mass experience a force of gravity in the direction of the field. So it does, in fact, particle 1 experiences a force downward in the direction of the field. What about particle number 2? It experiences a force, Ethan, upward, opposite to the direction of an electric field. If it was positive, it would be in the same direction as the electric field, but a negative experiences a force opposite to the electric field. What about the third particle? Particle number 3 here, that's a negative in a stationary in a magnetic field. What happens to that one? Stays where it is. There's no force. What do you have to have for a charged particle to be affected by a magnetic field? Movement. F is equal to Q V, B. If V is 0, there is no magnetic force on it, right? So this one goes downward, this one experiences a force upward, and this one experiences no force. Let's go to particle 4 now. We get a negatively charged particle moving to the right through a gravitational field pointing downwards. Does it experience a force? Yes. Which way is the force? Downwards. So what's the shape of that path going to be if it experiences a force downward while it's got inertia to the right here? It's going to be a parabola. It's going to look something like this, right? What about this one in the electric field? Negative particle moving to the right, field downwards. The force is going to be upwards. What's the shape of that path going to be, Maddie? That's going to be a parabola as well. It's going to be the exact same thing as this, right? Except curving upwards instead of downwards. Both parabolas. What about particle 6? Negative particle moving this time in a magnetic field. Does it experience a force? Yeah, when it was at rest, it didn't, but when it's moving, it does. Which way is the force? Force is going to be downwards, right, according to the hand rule. Thumb, fingers, palm points downward. What's the shape of that path going to be? Not a parabola. It's going to be a circle. Make sense? This charged particle in a magnetic field will experience a magnetic force that causes it to go in a circle. Remember we said thumb, fingers, palm, and then it's going this way, thumb, fingers. Oh, sorry, you're right. No, you're right. It's not curving downwards at all, actually. Thank you. It is going to go in a circle, but it's not curving downwards. We'd say thumb, fingers, palm points out of the page, right? So it would go in a circle, but it would be a circle like this. A circle like this. Thank you. Ask that question, right? If I make a mistake like that, ask that question. It's not curving. It does not experience a force in the direction of the field. Not at all. It has to experience a force perpendicular to the field. All right, problem or particle 7 here. Moving downwards in a gravitational field, the force is going to be downwards. Particle 8, moving downwards in an electric field, the force is going to be upwards. So it's going to slow down as it moves downwards. Eventually, it's probably going to stop and then start going upwards, start accelerating upwards. What about this one? Negatively charged particle moving downwards in a downward magnetic field. Force is going to be 0 because a charged particle moving parallel to the field experiences no force. Make sense? All right. If there is a force on this one, the force would be m times g. If there is a force on this one, the force would be q times the value of the electric field. And if there is a force on this one, the force would be qvb. But we can also, because that's going in a circle, we could also set that equal to mv squared over r. There we go. We had 3 multiple choice questions that you worked on for homework last night, number 80, 81, and 96. Let's take a quick look at those multiple choice questions now, please. Number 80 says the speed of the proton. This is real similar to what we did at the end of our quiz, right? Speed of the proton, you have the energy. All we're going to do is say EK is equal to 1/2 mv squared. Make sure you convert this to joules and plug its value into here for EK, solve for V. When you do that, 2 EK over m, square root it, you end up getting 4.14 times 10 to the 5 meters per second. So the answer for number 80 would be A. The strength of the magnetic field tells me it goes in a circle. I'm going to say FC is equal to FM. I'm going to say mv squared over r equals qvb. I'm going to rearrange this to solve for the strength of the magnetic field. V's cancel, one of them does at least. So I get mv over qr equals b. I think when you do the math there, b works out to be 1.20 times 10 to the 1. 1.20 times 10 to the 1, which would express an ABCD answer as 1201. And we also finally had 96 to go over as well. 96 asks for the radius, the ratio of the radius of the alpha particle's path to the proton's path. We did a question real similar to this already on our worksheet. Ratio, compare, what's the word that comes to mind? Divide. So we're going to say the radius of the alpha particle's path as compared to the radius of the proton's path. We know that radius, if we rearrange the equation, FC is equal to FM, R is equal to MV over Q times B. So let's replace R alpha with MV over QB for the alpha particle. And let's replace R proton with MV over QB for the proton. Tells me that the magnetic field is the same, I think, right? Same magnetic field, yeah. Cross that off. It also tells me that the speed of the alpha particle is twice the speed of the proton. Watch what I'm going to do here. I'm going to replace the speed of the alpha particle with twice the speed of the proton. Is that okay to do that? Tells me that it's twice the speed, so why can't I set it equal to twice the speed? Now, this cancels out. Simplifies it a little bit more. Now you can plug in your numbers here if you want. You got the mass and the charge of both of those particles, but there is a bit of a shortcut here if you spot it. The mass of the alpha particle is 4 times the mass of a proton. And the charge of an alpha particle is twice the charge of a proton. If you don't spot that, that's okay. Just plug in your numbers that you're given on your data sheet. But if you do spot it, it makes life a lot easier for you because Q cancels, M cancels, and I'm left with, oh wait, no, 4. I had another 2 on the top, right? So I end up with 4 times 2 divided by 2 is 4. So what's my ratio? 4 to 1 there. Okay, plug in the numbers. I don't care. Just means you have to punch them into your calculator as opposed to doing them in your head like I did there. Right? 2 times 4 times divided by 2 is, it's a pretty easy mental calculation, I think. Bless you. Good there? How many people got this one right? Okay. Okay, let's do a quick little review of what we did yesterday with the generator effect, and then we're going to move on to this whole notion of Lenz's law. That's our last thing. Warned Connor yesterday that I was going to have him volunteer yesterday using this concept of Lenz's law. All right, just a little refresher here on this whole electromagnetic induction thing. Let's say we've got a magnetic field. It's pointing down the page toward the bottom of the page. And let's say I've got a wire going through that magnetic field. There's electrons inside that wire, and those electrons are moving to the right because of a battery that's hooked up, because of a power plant that's hooked up to it, a solar cell that's hooked up to it, whatever the case may be, Ethan, right? We know that this particle is going to experience a force. Thumb, fingers, palm's going to point outwards. We also know that the wire itself will experience a magnetic force out of the page. And we can find the value of that magnetic force by using F is equal to ILB. Okay? We've done that. Nothing new there. But yesterday, we looked at what would happen if we had that same magnetic field, say pointing out of the page. We have that same wire with those same electrons in it, but this time the electrons aren't moving because of a battery or some kind of power supply or a solar cell. They're just sitting there. In other words, you don't have a power supply hooked up to it. You got a wire, a non-ferromagnetic wire, just a piece of copper sitting in a magnetic field. What happens to it? Nothing. And there is no electrical or magnetic effect whatsoever. But let's start moving now. Let's start moving the particles. And to do that, because they're inside the wire, we're going to have to move the wire itself. The particles here were moving to the right because of a battery. The particles here are moving upwards because I pushed them upwards. Maybe I pushed the wire upwards with my hand. Maybe it was steam that pushed it upwards because of a coal-fired power plant or a nuclear power plant. Maybe it was water that kind of got funneled around to push it upwards like a hydroelectric dam. Whatever. The wire is moving. Okay, what happens when the wire moves? Well, the protons and the neutrons inside the wire move as well, as do the electrons. Now, these electrons are moving upwards. If the electron is moving upwards, oh, that's a bad example, actually. If the electron is moving upwards and the magnetic field is downwards, what's going to happen? Absolutely nothing. But if I switch it around, here so that the magnetic field is into the page, that's the way I should have had it to begin with. And this wire with the electrons is moving upwards because I pushed it upwards or because steam pushed it upwards or whatever pushed it upwards. Now we can get a magnetic force on these particles. We're going to say thumb upwards. Why? Because the particles are moving upwards. Why are they moving upwards? Because I pushed them upwards. It doesn't matter why they're moving upwards. They're moving upwards along with the wire. They're not leaving the wires. Just push the wire upwards, the electrons go with it. Thumb in the direction of the particle, fingers in the direction of the magnetic field into the page, palm points to the right. There's going to now be a magnetic force acting on these particles to the right. What happens to the particles as a result of the magnetic force to the right? They move to the right. So now these electrons are moving to the right inside this wire. What do you call that? It's electric current. It's electricity. Right? It's electricity. This happens all the time. In just about every bit of electrical power generation that comes into our houses, it's generated in this way. Now, about 50% of the energy that's generated in Alberta is generated by burning coal, which is environmentally a horrible thing. Okay, all these greenhouse gases that it releases. In the end, we burn the coal, creates a lot of heat, right, Ethan? Creates a lot of heat. And as it creates heat, it boils water and turns water into steam, and then steam rises and pushes a wire through a magnetic field. It turns a turbine, really is what it does. But that basically moves a wire relative to a magnetic field, generates an electric current. In Ontario and New Brunswick, we use nuclear power plants as well as hydroelectric power. Nuclear power splits the atom, creates a lot of heat, boils water, generates steam. Steam rises, turns a turbine. Just does it in a lot more efficient way than burning coal does, with a lot less CO2 released. In fact, zero CO2 released. Unfortunately, you get this nasty um, radioactive waste to deal with afterwards. But we'll bury that and let our grandkids worry about it, right? Um, they do actually. I mean, what do they do with it? They do bury it actually, and they encase it in concrete, put it in a mountain. And there's a hollowed out mountain in Colorado where a lot of nuclear waste goes. Um, yeah, yeah. Um, Bottom line is the electricity is generated in the same way. Even wind power, right? We generate a lot of wind power in southern Alberta. Wind comes, turns a turbine. What does it do in every case? It moves a wire through it relative to a magnetic field, and that generates an electric current. So wind power generates electricity in exactly the same way as nuclear power does. It's just a matter of where we get the energy from in the first place. Wind power, it's the kinetic energy of the wind. With nuclear power, it's the energy stored in the nucleus of an atom. But ultimately, the electricity generation itself is exactly the same. You move a wire relative to a magnetic field, you generate a current. The exception to that would be solar power, which we don't generate solar power on a widespread use here yet. It's coming probably, but right now, anybody who has solar power, it's likely just literally on the roof of your house as opposed to on the power grid, right? Yep. It works on a completely different principle where you've got the energy from the sun liberating electrons from a material. So a completely different material. We'll talk a little bit more about that in our next unit, though.